Thank you very much. So yeah, so today, just going to be doing a talk about reducing compile times in Xcode. Yes, the struggle is real. It's a bit of a, compilers and compiler theory, bit of a dry-ish topic, but I've been told this is a really good talk, so I hope you folks enjoy. So this is just a brief, quick overview of what we're going to be going over, just a bit more about me and myself and some of the things that I've done here in Toronto and beyond. And then we're just going to do a brief theory of compilers, some references at the end, common iOS Xcode compiler issues, and a process for moving forward, sort of a way to get out of the weeds if you are indeed experiencing longer compile times with Xcode or Swift, or if you're using another compiler. A lot of this has overlap outside of Xcode, and we'll be discussing that. So about me, so currently I am working at Loblaw Digital on their iOS platform as a staff developer. It's a very interesting role. I've met a lot of interesting individuals, and I've really gotten to know their code base and focused just on sort of all the aspects from a very high level. Saw a lot of challenging problems. It's a great place to work. And, I really recommend checking it out if you're, have the opportunity and about, Loblaws and what they sort of do. I'm also building a company called Potcat Incorporated, which is a production and manufacturing company. We're doing a lot of really interesting things. I've actually just got a prototype here for some camera equipment that we've got and we've 3D printed. It's pretty interesting. We're using basically like materials that you can just throw in your recycling bin, and we're looking to basically build a product that has electronics in it, anti-fraud device built into the lens cap, actually printed into the lens cap, and we hope that that's sort of our first breakout product. So it's really interesting there. Always looking for like-minded individuals. Feel free to hit me up on social media. I'm definitely DM friendly and will probably respond. It might just take me a little bit of time. Basically, here's how to contact me. This is just my business card. Feel free to reach out either via email or one of the social media links. The Potcat Inc. is more corporate focused, and at SK Larose is basically on Twitter. It's just random things that I have or haven't posted. And most of the sort of photo or video-based social media that we're on, the personal accounts, more just focused on like photography with some film work, not too much about me as a developer, but doing events like this gives everyone a great opportunity to learn about that. So let's jump into it here. So to understand why compile times increase, we first need to understand compilers themselves. A lot of devs, don't really dig deep into there. They don't really look at, what your actual compiler is doing. So we're gonna tear apart that black box. We must actually step outside of ecosystems like Swift or Kotlin and look at compilers in general. Why do we get issues with compile times? What are some of the problems that are common throughout, every compiler based on the underlying technology? And what are some of the problems, that mobile devs using technologies like Swift and Xcode will run into in modern development? So we need to ask ourselves, why do compile times get long in the first place? And more specifically, what exactly is a compiler? This might seem like a very sort of easy question to answer, but when you really think of it, humans, we're familiar with a lot of various patterns. We often, throughout human evolution, we've gone and we've taken those patterns and we basically formed languages that are great for writing down and that are great for verbal communication, right? So we use the vocal abilities of humans and we use the pattern recognition that our species has sort of developed over time to make things that are easy to verbally commute and to sort of write down. Computers, not so much the same. Computers operate on bytecode, or more sort of generally instruction sets, right? And these are sort of languages or sets of patterns, that say, okay, move this value from this register and go and, put it here, right? And you have certain things, you have a lot of hex values. You're talking about things like Intel x86 assembly, and just this very, very, very low level set of instructions that are very, very, very tough to actually do meaningful things in code with. That is why we've gone and we've developed modern programming languages. They basically bridge the gap, right? Most programming languages that individuals, especially in this call, deal with, you could probably annotate them with some comments and read them out to the point that you could probably have someone who is not as initiated in programming as you are, and they would kind of sort of understand what's going on. We basically created these sort of almost human languages that have a lot of mathematics and things that we're familiar with seeing through just most educational programs in various cultures and whatnot. And we can sort of transcend that and create a language that humans understand at the top that can be transferred by compiler into an instruction set or something that the actual processor or hardware understands. So how do compilers actually function? As I mentioned before, the main functionality of a compiler really is translation. It takes human readable patterns and syntax, that's modern programming languages, and it enforces certain rule sets and then basically converts that to machine code, something that either the hardware of the computer that you're running can understand, or a virtual machine or some sort of mid-tier or intermediate layer can basically process into hardware readable instructions. It achieves this through two main concepts, tokenization and multiple recursive passes. So what that basically means is at a very high general level, your compiler is passing through your project source code. It's basically breaking down certain aspects of your source code into what we would call tokens. That's the tokenization phase. And then it's checking to see if these tokens follow specific rules. And it does that over multiple times, right? So each time it goes through a specific scope, whether that's a file or a module, it goes and it pushes tokens to a stack. There is an actual data structure stack in most compilers that it pushes them to. And then after it leaves, it basically pops them at the end of the phase and checks to see if all of the rules match up. Each time, what it sort of does this sort of back and forth where it pushes to the stack in a specific order, and then it pops everything and checks to make sure that the tokens before and after it abide by a very specific set of rules. A really interesting point is, I assume that there's a lot of iOS devs on the call. You may have seen at the bottom of the screen here, you've got 36 out of 324. You may have sort of seen numbers like this flash as you're compiling your Xcode project. And often what that's actually telling you is it's describing a specific phase that the compiler's in. So it might have, pushed 36 out of 324 tokens. And then it's sort of it making its way recursively through the project, which is why you'll see the bottom fractional number change. It'll change to 1,000 or 200 or 20, and then each step it's basically doing this sort of push pop and applying different rules. And each phase does specific things, like oftentimes compilers will have a phase dedicated to making sure your types are correct. So it'll be checking, okay, can you add an int and an int? It'll be doing things to make sure that variables are in scope in another phase. And it's basically constantly doing this in a recursive manner. So let's get into an example and actually see this in action. So the old add example, right? Very basic. I think this example has been used as long as there's basically been literature surrounding programming manuals way back in the late 80s and early 90s, all the way to those thick books. I'm sure if you have any parents who have ever been in any sort of technical development sphere, they've probably got these old C++ or C primer, and you always see this classic add example. So we're going to be going through how a compiler looks at this, and of course this is in Swift, and let's take a look. So what we're going to do is we're just going to do a sort of generic compiler phase and sort of describe how it goes and actually adds the tokens and applies the rules. So if you're looking at a statement like this, your compiler would basically go through, it would find a C token, right, the actual variable, it would find an assignment token, it would find a result token that's actually intended to basically capture the result of A plus B. Then it would find an A token, push that onto the stack, and then a plus token. And finally, it would probably push a B token as well. I won't get into what would happen, just for simplicity's sake, what would happen around the return statement, but it's very similar. It's just basically saying you're exiting scope, right? So your stack would sort of look something like this, where you have your classic first in, last out. So you've gone and pushed the C, then your assign, then the result, then A plus B. It's fairly simple, fairly straightforward. The compiler then, of course, pops it. So what it'll do is it'll go through and it'll pop each token. So it'll pop your B token, then it'll pop your plus token. And as it's doing that, it's basically checking to see, okay, does A plus B, violate any of the rules that we've set up, right? In this language, are you allowed to add, A to B if A is a string and B is an integer? Most languages, that would result in a syntax error, right? So it's basically checking different aspects of syntax through the different phases that it goes through. So it goes through this by scope. So you'll have a stack for your entire class or a larger method. And as it goes into a sort of smaller or more specified scope, it creates a new stack. And then in a specific phase, it'll actually go and check to see if those tokens are there, basically giving you your out of scope errors. And as I mentioned before, it does this recursively. So after it does a first phase, it usually checks a specific set of rules. One of the more common ones in compiler design are things like, checking to make sure that you don't have any type mismatches. As I mentioned before up here, what happens if B plus A, B is a bool and A is a string? Certain languages support adding that together. They have shorthands for, converting bool to a string or something like that. Swift, on the other hand, that would be an example of a syntax error. So type checking is something that's done in a specific phase. It'll then move on and basically iterate back through your code, and it'll check other rules on another phase. So it's sort of constantly doing this recursive dance where it's sort of edging through the scope, adding tokens, pushing them onto a stack, popping them, and ensuring that all of the tokens themselves actually abide by the rules set out for the syntax and for the language that you're working with. Fun fact, so many of you who are familiar with Xcode and Swift and even Objective-C have probably seen things like this inside of your projects at some point, right? Where you have hash if some sort of value else, and then you have an end if, right? In the C programming language, we actually call these preprocessor macros. This is a really interesting sort of name for this concept, as it is very fluent in a number of different languages and has been reused basically everywhere, improperly some places, more so than others. But yeah, so what this is actually doing is these sort of special keywords that you have here, hash if, hash else, hash end if, those actually get evaluated in a specific pre-compile phase when your code's compiled. That's why in C they're called preprocessor macros. So if you notice something interesting, you can actually write code using these in a way that violates the syntax. If we didn't have the statement wrapping these two lets here, this would be a multiple declaration syntax error. But because this is evaluated before any of the other steps, your compiler is actually omitting the code that is in the logic path that isn't compiled. So if you're in QA and you want to add a QA app delegate to your project, the app delegate that would usually be used for production never even gets initialized. That code isn't even compiled into the compiled source code or the executable code. It's actually omitted, and then you can do things like this because, as far as the compiler is concerned, that code those tokens don't even exist after that specific phase. This can obviously cause some problems, and as I mentioned before, this has been misused and was actually identified as a major problem with the C programming language. We still use it today, but mostly correctly in modern programming. But it's interesting to note that because this is done in a very early compiler phase, you can basically write code where, it's ignored by the compiler once it gets to actually checking the syntax of the individual tokens. So if you're looking for more information on compiler theory, I really recommend checking out the work of James Cordy. He's a professor at Queen's University, and he's actually the reason that I have a somewhat good understanding of this topic, as he was my teacher and they actually forced me at Queen's, unfortunately, to build a sort of small, very, very, very lightweight compiler for a Pascal variant, the language Pascal. And you go over all these concepts and you see, how tokenization works, how to use recursion, and sort of how to step through certain parts of a language and build it. He has a lot of, there's a lot of supporting work in this field as well from Charles Halpern-Hamu, a professor at University of Toronto. Apologies if I got that name wrong. And David Wortman, another professor at University of Toronto. I also recommend, if you are interested in compiler design, I've done a very high level description of it. And before we get into the more Xcode and language specific aspects of longer compile times, definitely check out TXL. It's a rules-based language that allows you to rapidly design a compiler and a rule set, and SSL, which allows you to define. It's a language that's specific for allowing you to define specifications, and it makes a great sort of rules engine to define what your syntax and what the syntax of your tokens you want it to be. So if anyone's ever interested in just learning more about the compiler theory, it's a bit of a dry topic. I tried to stay as broad as possible. Definitely check out some of these folks online. So why is your project slow? At a very high level, there are basically two reasons that a project will take a long time to compile. So we basically have we can put these two problems into two different sections, right? Problems that are common to all compilers, problems that basically affect how I've described, the black box of the compiler working with tokenization and whatnot. That's things like long methods, runaway imports, duplicate code. These traditionally cause that sort of, push and then pop and check rules. That sort of breaks apart when you have, incredibly long methods and whatnot. Problems that are language specific to iOS, complex closures. iOS has a very unique way of sort of dealing with closures, especially at compile time. And that causes some problems. Special or complex operators, especially when they're self-defined. And a lot of the syntactical sugar that we actually see on top of languages like Kotlin and Swift actually if you don't use it properly, you can actually run into some problems with increasing your compile times, albeit mostly very small, very marginally. But it definitely can get you in some trouble, and especially if you have a project that has requirements that that require you to write code in a way, or do certain things, on certain hardware, and your workflow, your compile times are being bogged down. You probably want to avoid some of these syntactical sugar that make regular developers, regular code bases that don't have these problems much more easier to deal with, right? Another one that I've also mentioned in problems that all compilers have, because Swift and iOS do this specifically poorly, is poorly managing your dependencies. Swift package manager is still sort of on the rise. We use it, and we still have some problems with it despite it being out for a while. And we still also sometimes use CocoaPods, Carthage, and Swift package manager. Still, all three of those solutions, even the native one, don't necessarily do the best job at dealing with dependencies. They just kind of assume that developers and teams fit in this sort of very narrow path where maybe they're only pulling a smaller subset of things, or they're not pulling in specific types of packages. But when you get into more complex projects where you've got remote frameworks that you're working on, and you're pulling in 50 to 100 CocoaPods, and you've got one or two things in Swift package manager, it can really affect it, especially within the Xcode iOS/Swift ecosystem. So getting more specific here, when we query the community, we see a number of similar problems that are constantly talked about within various blog posts and within various online communities. So I've just added some links here. Feel free to go and check some of these out. But they basically describe there's I'd say maybe 4 or 5 recurring problems that keep coming up, and that's what we're going to be discussing in the following slides. And you can definitely see there's a lot of overlap, and there's definitely a sort of smaller core subset of problems that seem to cause basically everyone at least once or twice in their career to run into problems compiling a Swift project. So given the context that we have for how compilers actually work at a high level, you're constantly taking tokens, parsing them, putting them onto a stack, popping them, checking to see if the rules are followed. And also given the context specific to Xcode and iOS, I feel confident we now have the knowledge and understanding to really understand why some of these issues become problematic and form a proper solution to some of them. So overlap and commonalities in the articles and in the community. Imports, dependencies, and framework. Like I said, massive problem. It's a big problem with most languages. However, working with Java, working with JavaScript specifically, and seeing some of the solutions that have cropped up within the community in the last few years, I would definitely say that there are some community-specific, platform-specific problems on iOS and Swift that deal with the dependencies. Long methods, reuse code, and dead code. That's another common problem that we see. Type inference, which goes back to the syntactical sugar that I was talking about. Complex operations and one-liners. This includes complex Boolean expressions, massive code smell. We see this a lot in our project. This is in your project. Don't worry. Clean it up in refactoring. But this could definitely be a reason why you're experiencing longer compile times. Use of constants and lets instead of vars. May have worded that very oddly, but using vars over lets or introducing an unnecessary amount of mutability into your classes or your modules, that can cause longer compile times as well. Overuse or improper use of specific operators. You can get into some trouble with complex Boolean logic operators. Sometimes using the I think it's called coalescence in Swift, the double question mark operator. I'm not 100% sure. Sometimes using that, if you overuse it, or if you've got a complex line that's got like 6 or 7 of those in that can be a sore point for your compile times. Large or numerous storyboards. This is super specific to Xcode and iOS, and hopefully Swift UI eliminates this completely. Overuse of extensions and global object modifiers. That's sort of a specific one and kind of hard to explain at face here. So let's wait until we get on that on another slide. Unnecessary or long build script. Also something that is very specific, but often comes up as something to check when you're looking to reduce compile times within the online communities. So let's get into it. So imports and dependency management. So there are a lot of problems that can come around by misusing your dependency manager. So you could have old or different versions of your dependencies. That usually happens when you're working with CocoaPods and there's a lot of, or even Swift Package Manager, and any package or dependency manager, and you have this sort of complex build surrounding it. And what happens is you basically end up in these situations where one thing has a requirement on a slightly older version or a slightly newer version, and you can actually end up with multiple versions of a specific dependency being loaded. There are a lot of sort of fail-safes under the hood in Xcode that try to avoid this, but it is something that still happens. We've notified a few things in our project, and if you think back to pushing tokens and sort of popping it, when you have multiple versions of something like RX in your project, you can add, you're adding 30 seconds, 20 seconds, an additional minute. When it goes in, it basically has to parse both of those dependencies. It has to push all those tokens. It has to do all the rule checking before it can give you that sort of thumbs up to say that your project's good to compile and it's built. Unnecessary dependencies, and sort of as a general concept, mismanaging your dependencies. Long methods, reuse codes, and dead space. So this one should be a no-brainer. The longer your methods are, the longer that your methods are, more complexity that you're adding per scope. You have to remember that as a compiler is going and adding things to that stack, it's doing it on a per scope basis. And that's important so that it can check to make sure that, a variable you've used in your method is that's an instance variable from a class that the method's contained in, that it is in scope, right? So if you have these incredibly long methods, what you're doing is you're basically building the amount of time, and you're also most likely increasing the amount of things that your compiler now needs to go and check to make sure that, okay, the method's using, a global variable in this class, an instance variable in the class that it is defined in, an instance variable that's public on another class, right? It has to go and do all these complex checks. This one, however, is incredibly easy to fix, right? When we start talking about solutions, things like fixing problems with your dependencies, that's a bit tougher, right? You've got to figure out a way to only have one dependency. That may cause a lot of problems in your manager. But long methods or overly complex methods, pretty easy to fix. Your standard refactor pattern, break it up, make the code equivalency of it, of the piece of logic, and put it into another method or class if the method has grown to the point that it could be its own class, and your compiler will thank you for it. Type inference. This is incredibly specific to Swift. So, and I want to keep in mind when I'm talking about these individual problems, the actual problem of long compile times is often an amalgamation of everything else. It's not just the fact that you're pulling in unnecessary libraries. It's not just the fact that you have long methods. So when you start seeing your compile times rise, it's when you want to start looking at these different problems, prioritizing them, and seeing what is and isn't an easy fix for it. So this is not necessary everywhere. Type inference. I am by no means recommending that you should go and add types in Swift to everything. Swift has a lot of syntactical sugar around that. That helps us do our job quicker, and that is a far larger payoff than the micro or milliseconds that you're saving by telling the compiler that this is an int or a string. So my sort of recommendation for this is basically what you have to do as a rule of thumb is if you have a complex one line and it's very unclear what the type is, if it takes you a few seconds or a minute to sit there in front of your laptop and try and figure out, okay, is this returning a string, an array, a dictionary, what's going on here? Then the compiler will probably struggle with it too. You have to remember it's going through and basically popping all these tokens onto a stack. You'll hear me say that a lot throughout this talk. And then it's basically going and checking if they abide by rules. When you have certain syntactical sugar or shorthands, things you can do to make your one-liners nicer. Type inference, Jeff definitely sort of goes under that rule. Then that's more rules for it to check. And when you make these overly complex statements like that, in some cases, it is a good idea to basically go there and add, okay, this is returning a dictionary, or this is returning, a dictionary of any and string or string key and any object. So that really helps your compiler out a lot. It doesn't have to evaluate that. You're basically short-circuiting the rules that govern a lot of this sort of high-level syntactical sugar that Apple's gone and given to us, right? You should look at type inference and a lot of these things that Swift just sort of does with its pre-compiler, which works in a very similar manner, as things that help you out. But you should also be aware that if you misuse them, they can contribute to longer compile times. Complex one-liners. This is very similar to your type inference, right? Like here we have an incredibly complex, this is just an example that I was using in another presentation. So here we have an incredibly complex one-liner, right? Off the top of your head, can anybody evaluate that for me? Or understand even, what exactly is being done here? Should check the chat here real quickly. Yeah, it gets pretty complex fairly quickly, and you can also see too, right, that we've got the so far comma next in, and then so far does not equal, and there's not even a return statement, right? We're using that syntactical sugar that Swift allows. If it's the only line in the closure, use the return statement. So this is probably hopefully as bad as you'll see it, but this is absolutely tell us what's being done in the some non-optional function body. Yeah, so this is if I'm not if we go through this, it's reducing the first element. I'm not quite sure. I'll probably have to sit with this, which is basically my point here, right? This has to be done, and the rules need to be checked through a very basic and simplistic stack, push, and pop scheme. Not super easy for your compiler, but at the same time, this may only add a millisecond or two to your compile times. But if you are facing compile times and this is everywhere in your code, this is something you might want to refactor at large. As I said before with the previous syntactical sugar, use your judgment. Sometimes nice one-liners that don't have return statements, that you know, they make things look a lot cleaner, and you can definitely make the argument that you know, we're willing to take the, you know, few milliseconds in compile time hit. But as developers, we should be thinking consciously about these things and looking at the trade-offs and making realistic decisions as to what we want to keep in our project. Looking at this one line, I would say probably refactor this into maybe 5 or 6 lines, add a return statement at the end of the closure, and you'll have a much better idea. Not only you'll have a much better time, not only with compile times, but as mentioned in the chat, you'll probably also be able to understand what's going on in some non-optional, which is a very complex sort of one line there. Larger numerous storyboards. So this is getting into the specifics of how the Xcode compiler actually works. So I'm not going to go too deep into why these are especially bad in Swift, but the short form is your storyboards are complex XML. In fact, we can make XML. There are a lot of programs that do it out there, a lot of platforms, a lot of frameworks, a lot of web frameworks that basically strive to make XML somewhat human readable. Apple and Storyboards and Xcode, they completely forgotten about that. They basically say, you know, sit and look at the UI. Look at the actual, look at the actual UI that's being generated. Try not to go under the hood for XML. That's great until you have a merge conflict. And then you see just how unreadable these XML files are. So we get these massively complex XML files that represent parts of our UI. They get compiled at a specific phase or part of a specific phase in your Xcode compiler process. And they have a different rule set. XML is its own language. It has its own rule set. So you're basically being forced to use a very complex version of XML with a very sort of vanilla, in my opinion, non-optimized XML parser. And then, you know, people wonder why, you know, they sit there and they stare for 2 minutes at their Xcode project as it says, you know, compiling this storyboard, you know, 1 of 200, because these things traditionally take a long amount of time to compile. If we think back to that example where, you know, we're pushing tokens on XML and sort of popping them off and making sure that the syntax is valid for it. You can get around this by optimizing your storyboards. There are a lot of ways to break up your storyboards. If you want to use storyboards, you can also use Swift UI, which the interface that gets generated from the code that you create is a lot more clean, and it's a lot more optimized because you're constantly updating it. Every time you add a UI component in code, it just needs to refresh, or if you hit the refresh button on it. So it needs to be quick. You can't sit there for 3 minutes while your UI that's generated by Swift UI compiles, because then nobody would use that feature, and Apple's very adamant that we do use that. But these are a massive problem with large compile times, and there are sort of different approaches you can take. But like I said, I won't go too much into the weeds on this. I feel like this could be a complete talk of its own. Certain things, though, at a high level, break your storyboards up, segment your storyboards in a specific way where you only have the storyboards for specific classes. If you think back of specific flows, if you think back to that compiler and what's it doing under the hood, pushing and popping a lot, checking rules, that's much easier to deal with if you have a bunch of small XML files that are nicely compartmentalized and don't have a lot of external dependencies, versus having one, you know, monolithic XML storyboard or 10 of those that, you know, basically cover your entire app. Overuse of extensions, and this is a touchy one. I got a lot of interesting feedback when I gave a very similar presentation at Loblaw on this. People love to use their extensions the way they want to do it. Extensions have a lot of different purposes. Organization of code, making things more readable. This sort of has critics on both sides that are sort of outside the context of this talk. Extending functionality. When you extend functionality, you know, to a string or a structure or you know, a base type, what are you really doing, right? Well, every instance of that object at compile time now needs to be checked to make sure that it has the ability to use that functionality. So if you go and add something to a string, when a compiler goes and pushes that token onto the stack, it now has to check that as a rule in the same way that it would, check to see if you were using, is empty or size correctly. If you go and put an extension of a string or an extension of something that's commonly used throughout your program, every single time that the code is compiled, those rules now need to be checked. Your extended functionality of your base data type, it needs to check that it doesn't violate any of the rules assigned to that base data types or data types in general. This can get crazy quickly, especially when you start doing things like adding default behavior, via extending a protocol, right? You now need to go and check everything that's using that protocol is also using the default behavior that you've gone and tacked onto it correctly when you're pushing and popping those tokens. It's often a very, very, very small amount of time that it adds because the compiler is optimized to do so. But if you overuse this pattern, it will increase your compile times to an amount that you notice it. How to stop that is by using paradigms that are a bit more traditional, things like old school OOP, where you're using class inheritance and whatnot. If you are doing that sort of extension with default behavior for a protocol, and also to avoiding extending certain data classes, or extending data classes that are inherited by a lot of different other types and whatnot. That's sort of how you get around that problem. So avoiding extending the functionality of view controller or something that is often subclassed everywhere else, or is subclassed higher up in the foundation, because then everything that subclasses that as well now needs to be checked that your newly extended behavior doesn't violate any of the syntactical any of the language rules, or any of the rules that are governed by the actual Swift or Objective-C syntax. So misuse of this problem within many projects is very common. As mentioned, for organization of code and readability, we definitely as a community, I feel like we misuse that a lot. And then also to just even the simple act of extending base types can increase compile times, often not to the point that it's too noticeable, but when you start doing things like extending protocols to have a default behavior on that protocol, and then you start putting the protocol everywhere, that can be problematic. That can cause noticeable upticks in your compile time, and that needs to be dealt with. I think that's a bit of a typo there. Apologies there. Unnecessary or long build scripts. Not unscary. Take my word for it. These build scripts can become very, very scary. Most build scripts don't need to be run on every build. If they're not properly implemented, if you're not properly, looking into how and why the build script is running, does it need to be run every single time we kick off a dev build? Does it need to be run, does it only need to be run when we go to prod? Does it need to be run if we're not connecting to our production backend? All these different things you need to think about. Build scripts can add a lot of time to your compile phases. They are executed in a specific phase. And they're also very, very, very error prone. You often have a lot of problems. They're tough to debug. You get someone who's new on the team, they're changing things in the build script. All of a sudden, the build script's taking a lot of time or throwing weird errors. Your build scripts can definitely impact your compile times and your build times. And there's something that when you do research on finding solutions throughout the community for this, they're one of the things that just keeps coming up as a sort of make sure you don't have, right? Check before you go any deeper. There seem to be a lot of compile times that get enlarged by a very large amount, unproportional to other problems that we have very quickly, just because the build script's not written properly or it's being run every time. So definitely keep an eye out for that. Super easy to fix. Put it in the right spot. Add some sort of preprocessor macros to those build scripts so that they're only ever run when you need them to run. So moving forward, this is great. We sort of defined all these problems. We've gone over a few solutions here, but really, what can we do about this, right? What's a process that we can do given what we've talked about regarding how compilers work at a very fundamental level and some of the problems that we see in the iOS and Swift community? Where do we go next? So the first thing that you want to do when you're actually solving these problems in real world is you need data, and more data. You need to take a data and analytics driven approach to this problem. So you've got to first identify the problematic areas inside of your code base. You can do this very easily. Xcode provides a lot of tools. They'll tell you the exact frameworks that you're working in. They'll tell you the exact classes, and some will even go even smaller into the exact lines that are causing long compile times. And you can sort of infer why they're causing long compile times and whatnot. So you need to record these times though. So if you find a problematic area of your code base, first thing you do is you try to find out as much about it, and you record the amount of time that it's currently taking, and then you start thinking about theories. So once we know, we act. So you basically form a theory as previously mentioned, and you say, okay, this is complaining. I suspect this is a complex one-liner. Maybe it looks like the one-liner that I showed before there. And basically what you want to do is you want to form a theory. Okay, let's apply the standard refactor of that. Let's break this up into multiple lines. And then you go using your knowledge of compilers and the discuss code smells, you refactor the code, and then you rinse, wash, and repeat. Rinse, wash, and repeat. What I'm talking about there is after making the changes, you need to check to see if they've actually had an effect, which is why I said record. You want to record the times that you have going into this before you make any changes. We're doing a very data-driven and analytical approach here. And then you want to see if your refactoring has changed it. So you want to get a metric specific to the area of code that you're checking. Xcode allows you to do that fairly well. We just use the out-of-the-box compile times analysis, and we would find an error. We would sort of discuss it with our team. People would pitch ideas. Yeah, this look at this one line. It's hideous. This is definitely needs to be refactored. We do the refactoring, and then we would basically go and check to see if it reduced the amount of time. If they've reduced, what you want to do is you want to put measures in place so that they don't come back. This is very specific to the actual teams that are working on this project. Every team has a different flow. Teams are run by people, not code. Every team has a different set of rules. Some teams like to use things like linters. Other teams don't. Some teams like to call these things out in MRs or pull requests. Other teams, prefer to, tap their buddy on the shoulder who sits beside them. It's really specific to, your team and your environment and what works best for you folks out in the field. But you want to put something in place to make sure that these compile times don't creep up. Whether that's adding, something to your personal style docs if you're using one, or to your linter, you want to put a rule in place, make sure it doesn't happen. If they have not decreased, this usually means that your initial assumption and hypothesis were wrong, and you go back to step one. So you try a different approach, a different refactor, and you keep track of that metric. Maybe this has actually made it worse, what you've done, right? And then we move on to the repeat step. So regardless of if we have a success or not, we always end up repeating, right? Why? Why do we have to go through this and repeat this? Well, just like a compiler takes multiple recursive passes, so do we as developers. We don't just go through it once, finish, one problem, right? One metric, and then move on. We want to constantly be looping through the project, constantly be looking for areas that we can succeed with this process, areas where it ends in us finding, adding a linter rule or adding, a mention to call this out in MRs or PRs, right? We want to get to that spot, and we want to recursively do that in a very similar manner to how your compiler actually steps through your code, right? You want to go through your code, figure the problems out, record the times on a case-per-case basis. It works, great, move on to the next project, the next few lines below it. It doesn't work, recursively iterate and go through that chunk of code until you figure out what's actually causing those compile times. As I say below, then repeat. This, honestly, and this is more of a personal take here, but this is really the only way that I've sort of seen how it's done. As I say here, this is the way. Every other way that I've seen, it either introduces more problems, or we sort of get to a point where we're just spinning our wheels and discussing theories, and we're not actually implementing it. The best way to actually solve large compile times that have ballooned and gotten out of control really is a sort of data-driven, recursive analytical approach, where you're just sort of chugging through and going through and reiterating and re-looking at certain problems and creating new theories with your team to try to reduce it. it is a sort of slow and tedious process. But we were able to have a lot of really good, solutions and results on our team only after a few months, right? We were able to find the worst offenders of these things, prioritize the bugs, go in there with theories. Certain things increased it, certain things decreased it, certain things were inconclusive. One person's machine ran it faster, one person's machine ran it slower, and we basically prioritized the major offenders, and we were really able to clean up our code base in terms of long compile times. So it's and it really speaks to refactoring and sort of refactoring at a higher level, right? Maintaining the code base is more than just reducing bugs. It's more than just having a readable code base. It's sort of this constant ebb and flow of trying to optimize your code base in new and specific ways that work better for your team or the developers who are currently working on the project. So how we code, how we choose to code, what we want to do, how our biases affect how we choose to code. Maybe we've had a professor or someone who said, one-liners are great, one-liners are at all costs, and then your project is full of those nasty, what was it, non-nil sum or something, that method that I showed earlier, right? And you've got to go through and realize as a developer that how you code, even if it's only a few milliseconds or microseconds, and it's not even really measurable, how you code over a long period of time will build up. It'll degrade the health of your project. It'll increase things like your compile times, and it'll require more tools or degrade the health of pre-existing tools when you sort of just think of it of refactoring and fixing issues like compile times as a one and done. So to summarize, to fix long build times, we first need to gather data on troubling areas of the code, identify the code smells, form a hypothesis, the how and the why. Why is this happening and what do we think will fix it? Make these changes, check our work to make sure that these changes were meaningful, actually did something, they reduced a real world metric, and then you've got to repeat. You're either moving on to another area of code or you're reiterating a new hypothesis. It can be long, it can be time consuming and sometimes feel tedious, but in the end, your entire team will benefit and you will have a much better, code base with less compile times and a far more productive team as well. So that sums up the end of my presentation here. I'm just going to quickly check chat and QA. But before that, I would just like to thank Women Who Code Mobile so much. And thank you so much, Navati and Ren, for giving me an amazing introduction. And also to Navati for giving me this opportunity to speak to you folks. Thank you so much. Once again, here is just my social. I'll just leave that up screen and just answer some of the Q&A questions here. Okay, so
thank you so much. No, thank you so much for doing this. This was amazing. And yeah, there are a ton of questions here. So yeah, Ren will go over that.
Yep. So we have one from earlier from, forgive me if I say this incorrectly, but actually your last name might be easier for me to say. Mayberry. Miss Mayberry said that how does long methods reduce compile time if it works, and will it need to be done, but like just split up? Did that make sense? How do long methods reduce compile time? Let's start there.
I think. Yes. Sorry to interrupt. I think they mean, and you can correct me, Akia. How do long methods reduce compile time if we versus like splitting up into multiple methods? Oh, and they meant increase. Sorry, long methods increasing the compile time versus splitting it up.
Yeah. So So the just talking about longer compile times as to specific methods and method scope. Yeah. So you have to remember. So the reason that longer methods or even just longer and more complex code increase your compile times, it's just because what's going on here is when you have a longer method, you have more complexity. As you have more complexity, because your compile is working off of various scopes, right? So you'll basically have almost like nested stacks, if that's sort of a good way, or recursively created stacks. It now needs to, let's say you have a massive method within a class that's using instance variables or property variables from that class, and maybe it's using a global in your project, and maybe it's also has access to, you know, a parent class and then another class. Your compiler now, when it goes and checks those rules, when it goes to check to see if the int in your global is consistent with the int in that long method, it then goes and needs to basically check for that entire scope, as it's already pushed a bunch of tokens on there. It needs to go, you know, 3 or 4 stacks up to basically check to see that basically check and see that that it doesn't violate any problems or any syntax errors. When you go and you break your methods up, what you do there is you reduce the complexity. You put your sort of methods all on the same layer scope wise. And then what'll happen is if you have one of those methods that's accessing a global, it basically goes into that single method, puts them on the stack, does a single check, rather than having it to do it for a massive stack that might have, you know, other method declarations in there. It might have other closures in there, which are new scopes. So by basically using method decomposition and breaking it up, it will make the compiler's job a lot easier. So I also want to reiterate here, this was more just as the original sort of context of this project was more just to get the developers thinking in the mindset of, you know, adding some grayness, adding some transparency to the black box that is a compiler. This is by no means a recommendation of how you should code every single time, right? There may be instances where long methods are the only thing you can do. And you say, okay, this is probably going to increase my compile time, but, you know, in a very negligible way. It's going to be microseconds, right? Nanoseconds. Who cares? Let's keep the long method. It's easier. It's readable. We're going to take the hit on compilers. When you have large compile times within your project, you need to be more aware of these things. It's not a strict doctrine that I'm trying to enforce here. It's more saying be aware of how these might affect your compile times. They may affect your compile times in a way that's so negligible, it's not worth doing anything about it. Leave the long method as it is. It's readable. It's not really has too many code smells, but keep in mind that that could be a potential source when you're sort of looking at your either your Xcode tools or your compile log, and you see that that class or that method has a 15-second compile time or something like that, right? That may be a good place to start from a hypothesis perspective.
Okay, great. Could you hear me? Yeah, right, great. So the next question we have kind of builds onto that one. It's about the build log. So how can we tell which part of our code is contributing to long compile times?
So I forget what aspect we use. I think it was just the build log, but we had a nice, I somehow generated, I apologize, I should have refreshed myself on this. The short answer is I kind of forget, and I really want to pull up Xcode right now, but it's got our actual prod code on it, so I can't do that. But yeah, there was a tool, I forget the name of it, and I apologize for not including it in this presentation. I think it was just, there's like a compile time tab in Xcode, and it gave us very detailed information as to what aspects. It was at first, I think, by like framework or section, and then we could expand and see on like a class basis. And then I think we also enabled a warning where you will get a warning in Xcode if you have a crazy one-liner like the one I saw before. I think that's actually how I found it in a previous project. And I think you can actually increase the sensitivity of that warning, and it'll go and it'll like your project will light up like a Christmas tree. But you have to keep in mind that you know, if your compiler is complaining about a microsecond compile time, then it might not be justified to do anything.
That makes sense. If you ever find the name of that compile time tab, I personally would also be interested in knowing, because that might help reduce some issues. So that would be a great
Was it the report navigator? I'm just trying to look it up myself.
I think so. We looked at it in our meetings. I apologize. I just I didn't think to add it, but I should have definitely had like a screenshot that had it and then just changed all the class names.
Yeah, we can always share that link later as well. Yeah.
All right, awesome. Which brings us to our next question, which is, does using linter also impact our compile time, our build compile time?
Yeah, so this is an amazing question. It shouldn't, but in our case, it actually did. We were using the Swift linter as a dependency, and it still is one of the major dependencies that were contributing to our longer compile times. So this sort of speaks to, so your linter shouldn't do these things, but yeah, anything you add on top of these sort of basic compile times here will actually go and it will add time, right? It's like something that people sort of seem to forget when they're, oh, this IDE is so buggy, right? And it turns out that it's the precompiler. Your precompiler, like the thing that gives you errors in specific classes, is basically doing that sort of push pop operation and doing a very quick syntax check. And when you sort of see laggy compilers that perform less better on older legacy machines, it's usually because that pre-compiler phase is taking so much time. And to bring that back to the linter question, if you have a linter that's basically running as your pre-compiler, checking your syntax to see if the rules that you've added in, it can very well, if you don't use it properly, impact your compile times for sure. Great question.
We have another question from Ms. Mayberry, which is, are there any alternatives other than subclassing? And does that kind of go against solid principles?
That's a great question. So it's like I mentioned before previously, none of these things, and I think a good rule to follow, this might sound a bit paradoxical, right? But a good rule to always follow in programming is try not to always follow rules, right? So solid, yeah. So it's all about trade-offs, right? If you have narrowed down that it is indeed your misuse of an extension that is going and causing half a second to your compile times, which is a lot for a single chunk of code when you really think about it, that builds up. And yet the only good solution you see violates the solid principles. By all means, have a discussion. What does your team value more, the solid principles or the 0.5 seconds that it takes to compile this code, right? And when I was talking about the extensions, I think the major offender are what's being talked about here, right? Where you add default behavior, you basically replicate class inheritance by extending a protocol and then going and tacking on methods that have like definitions inside of them, right? We found examples in our project where we were doing that and the base protocol literally was empty. So you could just basically find a type, put the protocol on it, and then you basically just get methods for free, right? It's like adding, and then your base like what's your protocol even doing? It's nothing. It's your square, it's your angle brackets, and there's no methods you have to implement. You're basically just going and trying to do something that's easier on the eyes for your classic sort of class extension, right? So yeah, so in most cases, yes, subclassing, if you want to add default behavior to a protocol and you've already got established methods, that's totally fine. It's probably not going to kill your compile times. It's probably not even going to be the worst offender. But if you're really trying to cut down on compile times and you're out of ideas, you may want to see that going and implementing, in this one area of your code, a more sort of traditional OOP approach, or even you can have there are other ways to sort of do this. You could have, a structure that just has a property with a closure. There are functional ways to do this sort of thing where you have that sort of subclass behavior that can be inherited and whatnot. Yeah, so that's a great question, right? And the honest answer is sometimes they do. Sometimes these changes you have to through talking with your team, you decide that breaking the solid principles in this one instance is more advantageous because it takes 2 or 3 seconds off of your compile times, and you're willing to live with that code smell. Where other teams might say, no, that breaks the solid principles. Please don't change that protocol inheritance pattern.
All right, awesome. That brings us to one other question about, actually, I wanted to pick up one question from the webinar chat as well. What kinds of things do you use CocoaPods for? This one's for Sherry.
Do you want specific libraries or?
That's a good question. How
do you use
mhm.
Yeah, we use it for a bunch of different things. We pull in, we have a very complex dependency structure in our project. I obviously can't say too much about it, but yeah, I probably couldn't list specific dependencies if that's okay. But yeah, we use it to pull in mostly very common third-party dependencies. We have a whole security team that tests those. We also use Swift Package Manager because we're trying to just use Swift Package Manager, but certain things don't work. And we've actually had a lot of problems pulling in our own frameworks that we either host remotely or local in the project. We've gone and compartmentalized some of our code into frameworks. So we use CocoaPod Swift Package Manager to sort of do all of that, depending on what dependency works best. I will be the first one, and Navati's definitely heard me complain. I will be the first one to admit that it is not an opportune situation. I would love to just have one package manager and just deal with the problems of that one package manager. So short answer to your question, Swift CocoaPods is doing too much right now, and we would love to get rid of it.
That's so funny. All right, great. And let's see, next one, I'll switch over to one more question from Ms. Mayberry. How do you record compile time other than setting a timer to return to Xcode after 5 minutes? How do you record compile time? How about that?
Yeah, so we had a very specific method set up to it, but I think we did. So yeah, so I'll sort of walk through because this is a really good question, and it outlines a real world problem that we had to solve, right? So initially, yeah, we were just using timers, and it would basically be like, okay, the first time it hits this phase, but you can actually, there's a way. So I'm trying to remember something from a few months ago. There is a way to do it with build scripts. I think it's a very high level way to say it. You can sort of, like I said before, you can if you know what you're doing and you know the ins and outs of Xcode, you can basically trigger a build script on any phase. So you can trigger a build script that starts at a certain point and then ends at a specific phase. And you can go through and do that. But there were problems with that, if I'm not mistaken. And we had a problem where we had to basically replicate this and have the other devs who hadn't spent weeks or months trying to solve these problems sort of in a vacuum replicate this. And I think we actually went with record from this phase to record from when this phase starts to like when you see something on your simulator, right? Because I don't think that the build script was very easy to upload to our source control and then have that duplicated. I think it caused problems, and I think if it ever accidentally made it into production, it had some really bad ramifications. So I sort of made the call there to just take it that it wouldn't be as accurate if we were using some sort of automated piece of tech. But there's definitely a way to do it. I think it was, I'm pretty sure it was build scripts. And there's definitely a way to do it where you could probably even just compile it from a bash script, or you could compile it from your command line. Xcode has great command line tools. And then if it's being done from command line, you can put it in a bash script and you can record the exact time you start compilation and the exact time the simulator gets kicked off, or the exact time it gets the build succeeded or whatever. So if you're looking to replicate this with your own team, I would recommend, although I have not tried it, not using either of the approaches we looked into, but definitely looking into command line tools via Xcode and putting that into a bash script.
Got you. All right, sounds good. Just a few more questions here. Have you tried Swift UI tables, and how would you make that compile faster if you did try it?
I have not had an opportunity to try this. I have had some issues with Swift UI being pre-compiled, like being updated as I go. But I haven't really dug into the ins and outs of Swift UI. I have noted similar sort of buggy or slow things or choppy things that don't quite work. And I would love to sort of dig into it from the perspective of what's going on in the precompiler. And another thing too, I try to stay away from like the exact implementation technology Apple does, but they're actually very transparent about it. So if you ever want to just sort of read about how these things work, go through the Apple doc, find the specific situation where you're seeing problems and try to make sense of it and see if you do things in your project that actually change it.
All right, sounds good. We have one other question. So is it better to use var or let and const instead of what was originally in your example?
Yeah, so I think I had that backwards, the example.
Okay.
I apologize. I apologize for that. Yeah, so I think we discussed mutability very briefly. But yeah, having sort of this more sort of functional approach was fairly popular a few years ago, but I haven't heard too much about it recently. I feel like a lot of focus just goes towards things like architecture. But yeah, there's like, if you actually look at like sort of like hardcore old school functional programming, right? It's supposed to be this very modular thing, almost like an extremist take on modularity. But you see the benefits of it, right? It sucks. Everything is in certain programming languages that are heavily functional. You can't make a var. You can't have these concepts, and you're constantly copying things around, right? But when you think of that from the perspective of a compiler, it makes its job incredibly easy, right? It knows that token is never going to change after it's assigned to once. The rules that it has to apply to that token, that variable token, are far smaller, even just from a mathematical standpoint, right? There's a far less subset of rules that can be applied to it now that the value can't change. Whereas if you have a var, you can go, and if the var is public or global, you can change it basically from anywhere, right? You can go and you can mutate that value if your class is public, and then now the compiler has to go and check every single instance where that's being mutated and make sure that it abides by the rules or the syntax that's governed for that token or variable.
Fair enough. And how would you go about verifying or checking like that is, I hope I'm not misinterpreting this question, Sherry, but for the question about how you go about verifying and checking those kinds of samples, those methods, how would you make sure that it was correct?
Sorry, would you say it's a, what do you mean by verify? Sorry, can I get some clarification?
Yeah. There's another follow-up question, which takes more compile time, let, const, or var?
I'm I feel like I'm in a coding interview here. I'm not. So I would assume another thing that we have to understand too is compilers are constantly performing optimizations. So there may be an edge case where this is optimized for, and sometimes those will be talked about in the documentation. Sometimes they won't. Sometimes that's part of Apple's secret sauce or Android, whatever, right? So if we completely forget about platform specific optimizations, I would say that while only using lets, make, or constants, I'm not 100% sure as to how constants are saved into memory. So if we just look at let and var, as I mentioned before, let is almost always easier to compile when you look at compilers at a very general high level. But when you look at languages like Swift, I've even seen it and I've even read about it. There is a lot of optimization code. And I did not touch on pre-compiler optimizations. And often, if you're doing that workflow loop where it's have a hypothesis, check to see, if that's true, record the time, and then sort of reiterate. If you come up with bad examples first, one of the things I recommend is looking at if there are compiler optimizations that would account for that. We ran into examples where we did things that through the very fundamental understanding of how a compiler works, that very sort of basic push pop paradigm that I talked about, it made no sense why a certain piece of code would actually compile quicker than another until we looked at some of the optimizations that the community had suspected that the Swift compiler was doing. And then it was like, oh, okay, they're optimizing for this, right? We ran into situations where certain syntactical sugar where you'd be like, oh my God, this must be horrible for the compiler. But then it's like, oh, because they use bool optimization where if it's an or, it doesn't check the rest of the statements. This actually compiles faster doing it in a way. So there is a lot of unintuitiveness inside compiler design in modern compilers. I probably should have touched base on that more, but it's kind of like a rabbit hole, I feel like, where people could be like, oh, but in the in Android Studio, the compiler is optimized for this, and the Java compiler does this when you're using enterprise web Java, and it kind of becomes this conversation of specifics. And I wanted to keep it very broad and generalized. But yes, what performs better? Constant, let, var. I would assume let. And I know that from as I mentioned before, the sort of basic language that we worked with in university, it had that sort of, it's that paradigm of constants and mutable variables being Pascal, and you could actually see, because you were writing the amount of rules that were being checked for those tokens, that you had to check less rules.
Fair point. So thank you for answering all of those. Last one, hopefully not, maybe not the last one, who knows? So why would you say that it's okay to use default implementations of protocols versus like a class inheritance if all the classes that conform to that protocol actually use the default implementations?
So I feel like I really have to look into just that specific question. My knee-jerk answer to that is, and I hope this is, I hope you don't see me start skirting away on this. So hold up. If all classes that conform to that protocol actually use the default. So I don't know. So let's first ignore optimizations, as I stated previously, right? And let's just focus on the basics that were discussed in this talk. Yeah, so I'm not sure if they're using all of them, if the classes that conform to the protocol actually use the default implementation. So are they using the default implementation, but then other classes are defining it? The whole point with the default implementation is that it now needs to go and check that that type is doing certain things properly, right? Or that it now needs to go and check, right, if you're extending like a string and providing a default implementation for something, sorry, a protocol, my bad, and you're providing like a default implementation for it, it now basically needs to go and check anything that you pin to it. It needs to go and find that default implementation and see that if that's being used properly in the context of that specific situation. So I feel like if you had it being used everywhere, the classes that conform to that protocol, yeah, I think if you had it, so I'm not going to say it's okay or not. You really have to, like I said before, you really have to see. It's very contextual to make these decisions. But yeah, I think if the question is just basically like what would compile quicker, I'm honestly really not sure if something's actually using it. I feel like if it's using the default implementation and you're not defining any new ones, then it'll only really need to check that once. I'd really need to think through how the compile token stacks would look on that.
That makes sense.
I apologize for not being able to provide a more definitive answer on that.
I apologize because we're a little bit like 20 minutes past, and I was wondering if you have a few more minutes to go over one last clarification question, or if you would prefer to be contacted via email for any of the remaining questions, if anyone has any remaining questions.
Yeah, no worries. Let's hear it. I feel like we might have some individuals with some compiler knowledge here that might eclipse mine. But yeah, I'd love to hear it.
So the clarification piece about that last one that I mentioned about like how do you verify that something is wrong. So they're mentioning that like long statement from that sum option function.
Okay.
What process would you use to break down the syntax so that you could verify the function does what you want it to do?
Sorry, was that so this one right here, correct? So was just a quick question to that. Was that a follow-up for the question as to like what would be the better default implementation, or are we just asking like how we would break this up to reduce compile times or just refactor it in general?
This one was about verifying, checking that it's correct, that it works the way you want it to.
This long statement. So like first and foremost, I would probably use, I'd first refactor this and then I would verify that this long statement does work. I'm not sure where I pulled this from. I don't think this is from it might be like something that I renamed or changed from our project. I was just to illustrate that these things are real pain for your compiler. Yeah, so I would basically break this up. I think it's called, when you look at like your standard refactoring practices, I think it's called Boolean decomposition, where you take because it is basically a massive Bool statement that's separated by the ternary operator, that question mark, colon, question mark, or sorry, question mark, colon, colon. Yeah, so I would basically break these up into 4 or 5, let's see how we got here, 1, 2, 4 or 5 different sort of like Boolean assignments assigned to that, and then have basically have a final return inside of there that goes and just returns this ternary operation with single variables for each bool. And that is technically easier on your compiler because it's far easier to check tokens in single assignment operations when you just look at this inside the scope than some massive one-liner that also is using certain syntactical sugar and the ternary operator, which many sources have said that that's tough, I think, on not just the Swift compiler, but other compilers as well. So it sort of compounds this problem. Does that answer your question? I apologize if that does not. We should maybe get a check to make sure that there aren't any other updates or clarification on that.
Okay. I think if that was all of.
Yeah, I hope that answered it. That kind of sounded a bit more like a refactor question, and I hope I answered that correctly or to the extent.
If that helps Sherry at all.
Yeah, I hope that. Let me know if you have a follow-up question or if you want to discuss that a bit more.
I think that would be all for questions. So thank you so much for joining today, guys.
Excellent.
And thank you so much, Scott, for hosting this. I think we learned a lot. There are definitely some key takeaways from this that I had to take notes on in order to remember it. But it's really useful. It's kind of crazy. I would love to see more live examples of it. That'd be really cool. And we'll definitely upload this talk to our YouTube channel for one. And it'll be posted on the Slack as well. Hope to see you guys on there. And we thank you for staying the extra time. It's about 26 minutes past. Means a lot. Yeah, so that would be it. It was so great seeing you guys. Thank you again for a great night.
Thank you so much for this opportunity, and thank you so much for everybody who came out, engaged in this, asked questions. I'm really fortunate to have this opportunity. Thank you so much, folks.
See you guys.
Thank you. Thank you, Ren. Thank you, Scott. Thank you, folks. See you then.